session, we will talk about the F test. I hope we have covered the uh, independent sample t-test already. And we have some slides pending for the pair t-test. So what I will do is I will just first try to cover this F test, and then if we have time, then we will move on to the pair t-test. I hope that will work, because this is actually an extension of independent sample t-test to more than two groups. I hope it will be okay. Can anyone give a response?
Yes, sir.
Okay, yeah. So yeah, we met before on the session probability, and today we will talk about the F test, which is most of the cases which is actually used via one-way ANOVA. So in the earlier sessions, we might have discussed a normally distributed response from two independent sample and how to do it with independent sample t-test. Now we will move on to one-way ANOVA. Yeah. So these are some of the terminologies, ANOVA research terminologies. In the analysis of variance, an independent variable is called a factor, which is actually a treatment group or any sort of any sort of grouping which we wanted to analyze. The group that make up with independent variables are called levels of that factor. Like suppose there is two different treatment with two different levels, like high dose and low dose. So totally we might have. Hello? Can you see the slides?
Yes, we can see. No problem.
Yeah. Okay. So yeah, that is what we call the levels of factors. So we in the normal case we will not see different levels of factors. We will see independent number of factors in the analysis. Yep. A research study that involves only one factor is called a single factor design, and a research study that involves more than one factor is called a factorial design. So when do we use ANOVA? When our research interest is to compare the averages of more than two groups, when we wish to compare more than two level, or when we wish to compare more than two levels of a single treatment. So these are the different situations we use ANOVA in our data analysis. So there are certain assumptions, just like any other statistical analysis. There are certain assumptions with ANOVA. The first one is independence of observations. Each observation is independently drawn from the population, which means that it should not be a repeated measure, like one measurement where we are taking measurements from a single person repeatedly over time, or or it should not be a measurement which takes from single person from left side and right side. So in sorts of design, we will follow a different approach for the analysis, but it is not used, otherwise not used there. One way ANOVA is not used there. So the residual errors are normally distributed. In other words, the samples are drawn from a normally distributed population. So we in our previous section, we see what is a normally distributed population or a normally distributed sample, and how we are going to test them. And homoscedasticity, which is actually each it is assumed that each group will have equal variance uh, according to, I mean, equal variance of with respect to individual grouping. Like, so if we have males and females and we wanted to analyze a certain uh, factor, how whether the factors are equal in both males and females. In the t-test, we have seen that the t-test will be the one which we are using. But if the variance of that specific factor, we assume that it should be same in both group for the ANOVA test. If it is more than two groups. So for males and females, of course, we will use the t-test. Yeah. So let's see how it works. So I tried to avoid maximum number of equations and just try to give a visual representation of how things are working when we are doing ANOVA. So suppose we have three different samples, sample one blue, sample two green, and sample three yellow. And all these samples have different means, say x1, x2, and x3. Let's assume that all of them are normally distributed. So this is actually a very ideal situation, but we rarely find it in real life, but yeah. Suppose, just assume that all the samples are from a common population. So we will have these sort of small differences in each samples because all of them are taken from a common population. So in other words, the assumption is all the sample means are actually coming from a population mean, which is represented by mu. So another scenario is at least one of them is from a different population. So we will get two of them from the same population and one of them from a different population. So in our assumption, we assume that this is the population we are taking from, and we see in the three different samples, we see one is not represented by this population. So or all of them are from a different population. So these are the different scenarios possible for a three group situation. When it comes to four groups or multi-factor design, then we need to look upon another way. But just for the sake of representations, we will assume that these are three groups and these are the three scenarios possible for our study. So this is our main population, and yeah, so these are called the between group variation. So if we assume, so if we take the mean of all these samples, we club all these samples and take the mean, it will more or less be equal to the population mean. But if we see group wise means, we can see that it is for the blue, it is much far away from the overall mean, like towards the right, and the yellow group, it is much far away towards the left, and the green group is almost identical but slightly towards the right side. So these these type of variation is called the between group variation, like the variation of group individual group means from an overall average, like overall assumed population, is called the between group variation. Between group variation is represented by how far each group compared to the overall average. And there should be one question which is arising, like, why can't we do multiple t-tests for instead of doing an ANOVA? Like, why should we complicate ourselves with new theories and when we can do it with two or three t-tests? So with an alpha of 0.05, there is a 5% risk of type 1 error. This is what we assume in our experiment. Thus, for every 20 hypothesis tests, you expect to make a type 1 error. Like you expect to reject a null hypothesis falsely in out of 1 out of 20 experiments. The more you test, the more tests you do, the more risk there is for a type 1 error to happen. So that's why we need to minimize our number of tests as low as possible to get a valid statistical outcome for our analysis. So this is called test-wise alpha level. The alpha level you select for individual hypothesis test, and experiment-wise alpha level is the total probability of a type 1 error accumulated from the separate test in the experiment. So if you see a real clinical trial papers or real type those kind of multiple objective papers, you will see this multiple testing corrections, Born-Frone corrections, and etc. So those are actually done to account for this multiple testing uh, probability errors. Like so when we do in a nutshell, we can say that if we are doing more than one test for with the same data for the same variable, we are highly likely to falsely reject a null hypothesis. So our confidence limit, when we say 5% level of significance, it might not be exactly 5%. So 3 t-test each, alpha is equal to 0.05, and experiment-wise alpha will be 0.143, which is actually very much higher, around 15 errors in 100, 100, 100 experiments, sorry, 100 tests. So, which is actually very high compared to the 5% level of significance we are claiming. So that's why we use ANOVA instead of repeated t-test. So then we discuss about between group variation, which I said the variation of individual means from the overall mean. So now what is the within group variation? Within group variation is the variation of individual observations within that sample from their own mean. So if you see blue sample, it has their own mean, like which is x1, for green x2, for yellow x3. So the variation of individual observations within that group is called within group variation. So what happens if within group variation is very high? So this is the point when we say that the sample size is an important factor. So we all know that when we increase the sample size, it actually helps to reduce the variation in the sample. So if our sample size is very low, or in other case, the actual dispersion measurement of that group is very large, you will see overlapping groups. Even though all those means are different, we will see that their within group variation is higher, and we cannot conclude anything about their outcome. So higher within group variation is actually fact favorable to null hypothesis. A lower within group variation is not favorable to null hypothesis. So what we say that partitioning of variance. So this is what we are doing to reach up to the F test. So we assume that the total variance as a sum of treatment and error variance. Treatment in this scenario, the grouping factor, whichever it is. So the total variation we see in those sample is a sum of between and within group variation. And the F ratio, F distribution is actually a probability distribution, just a continuous probability distribution, which is defined from 0 to positive side. So there is no negative value there. So the F distribution actually take account the equation for F distribution, sorry, equation of an F distributed variable, random variable F, is between variance divided by within variance. So as we can see from here, so if we have a higher between variance and lower within variance, or any of these cases, the F value will be higher, because between variance is on the numerator and within variance is on the denominator. So in the other scenario, so if the between variance is low or within variance is high, or both, the F value will be very low. So this will give us a statistics which can be linked with the F distribution. Because F ratios are computed from two variances, F values will always be positive numbers. So this one I told you before. Three different situations, numerator and denominator of the F ratios are almost same, so which will result in a value of 1. Numerator of the F ratio is much larger than the denominator, which is actually give you a value of towards the positive side, like greater than one value, so a higher value. Denominator of f ratio is much larger than the numerator, which will give you a value less than 1. So the numerator and denominator are almost same in this situation. So we can see that or the numerator is less than the denominator in this scenario. The numerator of f ratio is larger than the denominator in this scenario, because we can see that within variances are very low compared to the between variances, like the black or the assumed overall distribution mean to the individual observations in individual samples. So yeah, so in this scenario, numerator is larger than the denominator. In this scenario, denominator is larger than the numerator. We can see that the scenario is largely the individual variance measured in each group is very high, and we cannot judge anything on this kind of situations. So we will go into a case study. Suppose that psychologists want to examine learning performance under 3 temperature conditions, like 50 degree, 70 degree, and 90 degree. 3 samples of subjects are selected, 1 sample for each treatment condition. The subjects are taught to be basic material and given a short test, and these are the score of the test. So now you will have a doubt that whether the score is uh, normally distributed, or whether the score is um, to be considered as an ordinal variable, and which follows a certain different distribution. So just keep it for now, and just assume that this is normally distributed, and we can do our experiment with that. So here the factor is temperature, which has 3 different levels, like 50 degrees, 70 degree, and 90 degree. And our null hypothesis is that at least one population mean is different. So now null hypothesis is that all the population means are the same. So which is actually represented by mu1 equal to mu2 equal to mu3. And our alternative hypothesis is that at least one population mean is different from the overall mean. So let's see, there are some variability among the treatment means. Is it more than we might expect from a chance alone? So that is what we are exactly testing for. So you can see that for any experiment, it is highly unlikely that we are getting a perfectly equal scores for different groups. So what we are testing is that the difference what we see is actually existing, or something which is a chance of which is occurred only by the chance of randomness. So we can see that the mean for the first group is 1, for the second group is 4, and the third group is 1. So these are the 3 different groups we have defined. From the representation itself, we can see that if there is a difference exists, that difference will be on the green group. So the answer is very evident from here, but what we are checking is that whether the difference what we are seeing here is by random, or it is actually existing with a level of confidence. So the degrees of freedom for f value, we have seen that the f statistics is um, actually between treatment variance divided by within treatment variance. So there are 2 degrees of freedom. One is for the between, and one is for the within. So the between degrees of freedom, sorry, I don't think it's answered the question. So in the between degrees of freedom, we will see that we have 3 different groups. So the degrees of freedom will be 3 minus 1. So, and the within degrees of freedom would be 1 minus of that random sample. So we have, I think, 5 samples, 2, 3, 4, 5. So it would be 4 for the within degrees of freedom. So it actually leads to the fact that there are 2 degrees of freedom for the F test. Yeah. So the step by step, calculate each treatment mean and the grand mean and calculate sum of square between. And so I'll just give you a very fast session after here, because you are not going to do this analysis in a manual way. You will be using some sort of softwares, but I'll just describe it in a very quickly. So this will be the structure of ANOVA table. Just like I talked to you before, we have 2 considerations, like between treatments and within treatments, and the overall, and its corresponding degrees of freedom, which leads to, and the corresponding variance, and their statistics. So calculate each treatment mean and the overall mean. The overall mean is 2 and the individual treatment mean is 1, 4, and 1. So we need to calculate the sum of squares for within degrees of freedom. So sum of square 1 is 6, and sum of square of 2 is also 6. Sum of square of 3 is also is 4. So it is calculated within the group. And we need to calculate between deviation, just like I show you in the diagram. It is actually difference from the individual group mean to the overall mean, and we can see that it is -1, 2, and -1. So the square is actually 1, 4, and 1. So to get the sum of squares, we need to multiply it with the sample size. So we need to weigh it with the sample size. So this actually the difference of that individual observation, sorry, one observation from that within that group. So for the five, we need to multiply it with 5. So we end up with 5, 20, and 5. So the degrees of freedom would be k minus 1, which is actually 3 minus 1, 2. We discussed this before. Okay, so yeah, so between group variance means a summary of how much each treatment means varies from the grand mean. So the F statistic will be between group variance sum of squared divided by within group variance sum of squared. So 15 divided by 1.33, which is resulting into 11. So this would be our table. And yeah, this is the F distribution. So positively skewed distribution, concentration of values near 1. So values smaller than 0 are not possible. So it should be, should be a not possible there. So like T or F, it's a family of curves need to use 2 degrees of freedom, like degrees of freedom between and degrees of freedom within. For alpha is equal to 0.05, the critical value F with the degrees of freedom 212 is 3.88. So if our resulting value is 11.28, which is actually very higher than our critical value, so we can say that there exists the difference we have enough evidence to say that there is a difference in the population means of these 3 groups. So there is so what happens if we have if we find that there is a significant difference? So the next question we will be asking is like, if there is a significant difference, which are all are the groups which are significantly different from each other? So this is actually a second question. So for that we used post hoc multiple comparison test. So the usual one is LSD or Ponferroni or Tukey's. Tukey's actually similar to the LSD, Tukey's LSD test. So this is a small session about contrast test, which we can ignore. So this is what we need to do to execute the ANOVA. Just a sec. So we have another 20 minutes remaining, so I can just move on to SPSS and show you how to do it in SPSS.